Hello! Hi, Dante! Hello, hello! How are you? I'm doing kind of well. I guess I'm doing pretty well. How are you? Hi! Yeah! Oh, thank you for the hydrate. I will drink. Oh, 2 hydrates. Oh no! Oh no! I'm glad that someone's looking out for my hydration. Thank you. Okay, I'm gonna drink some more, guys. Ah. You're good? Great! That's very good to hear. So, today, I'm trying something new. I haven't done this before. Oh, the music just got really loud. Wait a minute. Maybe we should fix that. Okay, I'm just gonna turn that down just a little bit. No, that's still too loud. Okay, I think that's good. Yeah, so today I'm gonna work on my project because I have a lot of work to do. But I also wanted to stream, so I thought maybe maybe I could do both of them. Some people have expressed interest in seeing what I'm working on before, so I thought I would try it out. So yeah. I have a mild cough, but I think it's just allergies. It's something to worry about. It's complicated. I will fight those who aren't here. Thank you for being here. Thank you. Okay, so shall we begin? We shall. Okay, I'm gonna quick transition now. Here we go. There we go. Okay, I'm here. Look, this is my Google Drive. So I'm gonna create a new document, and this is just gonna be something like I'm gonna make it a title so that people who are coming in know what's going on. Oh, also I want to choose a fun font. This is not gonna be boring. It's gonna be great. So let's I want it to be fun. So okay. Here's something. Here, we can try that. What shall we? I'm coughing a little bit. What should we call it? super secret. Super secret science. I don't think I can make it more alliteration. I don't know. Project for for Chai's stream. Okay, so this is what we're doing. Oh, and we're gonna make it. Oh, it's not February anymore. It's March 1st, 2021. So, yeah, this is what we're doing. I will probably explain it, kind of re-explain it throughout as we, as people show up. I'll kind of go over what this is. Sorry about my cough. Yeah, so I should explain now. This is a bioprinting project. I want to be able to 3D print brain tissue. Now that might sound really difficult, and it is very difficult. But I think it's very useful. I think bioprinting, most people, I haven't seen a lot of bioprinting. Oh, wait a minute. Sorry about that. Yeah, a lot of bioprinting is with stuff like hearts. So, like, if you need a heart transplant, well, actually, that's pretty difficult to pull off, isn't it? I don't know. But you can 3D print organs to swap out with yours. In this case, I want to make some brain tissue, and I want the neurons to be laid out in a very specific way, so that you can make backups of your brain. So if you get a brain injury, you can just swap out the damaged part. Yeah, anyway. That sounds very bonkers. But yeah. Kind of is. um, my professor is interested in it, so I think it's a valid idea. I put your life in every self-promo channel I'm in on Discord. Oh, thank you. Thank you, Dante. I appreciate the support. So what we're gonna do is we're gonna go to Google Scholar. Neural bioprinting. So we're gonna find some papers and we're gonna cite them. So we're gonna collect a bunch of these so that we can use them in our research. So like here are some researchers who have done some of this stuff before, and I wanna reference their work in my paper or essay or whatever. See, look, 3D printing. Anyway, that's cool. So I'm gonna download it. We're gonna make a folder, and we're going to. We're just gonna wait a minute. I'm gonna check to see if my downloads folder is alright. I think what I'm gonna do is I don't understand any of this. That's okay. It's a wacky mad scientist project. I hope people can find this entertaining a little bit. I don't know. I'm just gonna mess around, and I don't know. I'm having fun with this. Oh wait. Wait a minute. Okay, so I'm gonna take everything. I'm just doing some file management back here. There we go. Okay. Oh wait, I have to do that again. Okay, here we go. There we go. Okay, here we go. Okay. So I'm gonna make a research folder. Research. Okay. X plus Y equals M is what I'm learning. Is that some algebra? Let's see. What am I doing? Let's actually just put this in here. So, pre-algebra, yeah. I'm taking calculus 2, and it's way harder. It's very complicated. Very, very complicated. Okay, so here we have this one cited by 83 people. Or papers. Yeah, papers. What about this one? Spheroids. Bioprinting 3D neural tissue models. So I want to know about the bioprinting. So what I'm gonna do is I'm gonna put this in the Sci-Hub and see if I can get. I'm gonna see if I can get access to this document. There we go. Yay! Okay, so now we're gonna download that. Okay. There we go. Okay, so now we have two papers. This one's from 2019. Hmm. This one could provide some stuff. Well, but what about this one? Ooh, this could be good actually. I don't know. So, I think this one, this one is talking about stem cells. So in this case, they're bioprinting stem cells, and then like those cells turn into a bunch of other cells. And that's actually exactly what I'm wanting to do. So that could be good. I just don't know if this is the best source. Oh, actually, it's been cited a lot, so maybe it's good. Okay, let's download it. When I see all these citations, like 127, it's like, oh, all these scientists read this paper and used it, and so it must be useful somehow. Yeah. Spinal cord injury. Citations. Okay. What about like the really recent ones from this year? The problem with this is that we can't see. Like there aren't a lot of citations, and so I can't tell which ones are like the best. Or maybe I shouldn't judge the quality by the citations. I don't know. I'm just like, this looks popular, so I'm gonna download it. What is this? What is a tubular composite? I don't know what that is. Macroporous hydrogel, tubular scaffold. Tubular scaffold? That's confusing. Oh yeah, I need to work on the chai latte command. I need to work on that. There's still... Yeah, I need to program it. Right now, that's all that I have. Ooh. Ooh. This one looks especially useful. Because this one actually is doing what I want to do, which is guiding neuron growth. Yeah. So let's see. It looks like we can't get it, so I'm gonna go to Sci-Hub. 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 It looks like the joke commands didn't work. Yeah, sometimes Nightbot doesn't notice when you put a command. So yeah, I don't know. Amma is lurking. Oh really? If so, welcome. Welcome, Sapphire. Wait, what's this? What is this? No, no, no. Oh, Sapphire! Hi, Sapphire! Welcome. Welcome, welcome. I should use my try hard command. I forgot to use that for Dante. Now it looks like Sci-Hub's not working so well right now. Because ACS Publications has noticed that we're using a website that is maybe they don't like. Sapphire says, I work because I'm working, but I care for you. Oh, thank you. Good luck with your work. Good luck. Good luck. Thank you for being here, Sapphire. Well, it looks like maybe we can't access this. I could log in through my school's library, but I don't want to dox myself. So maybe we can save this for later. Let's put this on the list. So we're gonna have a list of, actually let's make it bullet points, because those are prettier. Paid commissions? I need to figure out how to start commissions. I've had 2 people ask me now if I do commissions, and I really want to say yes, but I haven't figured it out yet. I have to figure out prices and then put them on my website and stuff. Anyway, let's see. No PDF acquired would be this one. Oh. There we go. So yeah, we couldn't find this one. That's okay though. But this one looks very helpful. Ooh, citations? Are there citations for it? It looks like no, there are not citations. But maybe this one cited some other papers that would be helpful. So we can do that. Okay. Additive lathe. 3D bioprinting of bilayer nerve conduits incorporated with supportive cells. Nah, not nerve conduits. Those are boring. I want to bioprint actual tissues. I want to 3D print a brain. Let's see. Nanogold induces anti-inflammation against oxidative stress induced in human neural stem cells exposed to amyloid beta peptide. Is that an Alzheimer's treatment possibility? Alzheimer's disease? Amyloid beta, gold nanoparticles. Why are gold nanoparticles so useful? You see them everywhere. It's like, wow, gold is actually pretty valuable, isn't it? You just have to get tiny nanoparticles of it. Okay, so neuro bioprinting didn't give us exactly what we wanted. So let's look for some more. Let's use some different keywords. Neuronal bioprinting. That might be the same thing. Except this time we'll see the word neuronal more. Which means it might be more focused on the individual neurons, which is what we want. Because we're looking at some advanced microscopic manipulation. Apologies for the cough. I drank a La Croix earlier today, and I drank it too quickly, and it made my throat really, I think it like inflamed my throat or something, and so now I have a cough. Anyway, Why do I say anyway? I don't know. 3D printable sodium hydrogel stem cell neuron differentiation. What is this? Ectomesenchymal stem cells. Have I been saying this word correctly? I've always said mesenchymal stem cells, but that might be wrong. That's probably wrong. I don't know. A lot of science words, I think I pronounce the wrong way because I haven't heard other people say them. So I learn about them online and then I get them wrong probably. Okay, this looks kind of boring, so maybe I won't reference this one. Although it looks like they're looking at a chemical thing, I think. Maybe? Oh, promote differentiation and growth. Oh, okay. So yeah, that's more of like a biochemical thing. Like maximizing the effectiveness of the hydrogel, the medium to grow the neurons. Eye tissue regeneration? That sounds exciting. Oh. What is this? What does this one look like? Advanced approach for eye tissue regeneration. Ophthalmology. Specific eye tissues can be custom fabricated. Just imagine at your optometrist, imagine if they had a 3D printer and it's just like 3D printing eyeballs. And then you go in and you say, oh, I'd like to replace my eyeball. And then they 3D print it. And then they swap it up. Oh, Sapphire, I think I told you about something, about another thing with like eye regeneration, but I don't know. That doesn't matter. Laser assisted? Yes, that's exactly what I want. Laser assisted. You see, I love lasers. Lasers are so helpful in science. Instead of just see, I think in the future, instead of taking pills to fix your problems, you'll shine some lasers at specific body parts, and it'll really precisely, like really accurately select, it'll target specific things and fix them, just like little things. And it's a lot better than just blasting your whole body with medication, because that has a few side effects usually. Not that I'm opposed to modern medication, but the future has some cool stuff. What am I doing? Oh yeah, okay. I'm gonna read through this. 3D bioprinting for eye tissue engineering. Look at that. It's an eyeball. Look at that. See, they bioprinted A cornea. They 3D printed a cornea. I don't know if this is actually useful. Oh, the retina. Did they bioprint a retina? Ooh. Solid orientation. Yeah, that's actually that's pretty helpful. I think maybe. Cell types orientation. Here we go. The cells of the retina need a very specific orientation to be able to carry their function properly. The correct orientation of the cells is one of the most difficult aspects to achieve when making a scaffold. Although the new approaches that will emerge over time might allow more precise control of cell deposition, 3D bioprinting already allows a relative control over cell orientation. This can be achieved by adjusting the printing parameters such as the printing orientation and layer thickness. Ah, I see! So they're saying they can just adjust like the nozzle where the material is going through, and then that can actually put down the cells in an orientation that's pretty good. That's kind of boring, but oh well. Also, yeah, this is more of a solid bioprinting method. So I'm more interested in laser-based laser-based bioprinting. Ooh, functional nervous system on a chip. That's exactly what I'm looking for. Let's see what this one is about. Advances in 3D neuronal microphysiological systems towards a functional nervous system on a chip. Allowed researchers to assess in 2 and 3 dimensions the functional interconnectivity of neuronal tissues. Ooh, brain organoids. They mentioned brain organoids. So those are kind of fun. They're basically mini brains. You get some stem cells, and then you tell them to become a brain. And then they turn into a tiny brain in a petri dish. And it's just like a small blob. And it kind of has the same layout as a real brain, which makes it helpful for studying. So it kind of lets you study the real brain by creating a mini brain. So like the mini brain is way simpler, but it lets you, it's kind of a model of a human brain. So that's pretty cool. I see, Dante is redeemed. Hydrate. Thank you. I shall drink water. I should probably drink some more water, actually. That helps me get my breathing back under control. Okay, what are we doing? Herein we will review advances in culture methodologies, focused especially on those of human tissues, which seek to bridge the gap from 2D cultures to hierarchical and defined 3D microphysiological systems, with the end goal of developing a robust nervous system on a chip platform. Yay! Okay, so this one looks handy. See, there's a brain organoid. It's a mini brain. It's just kind of a blob that it's kind of like a brain. Oh, here you see the laser. So this is the method that I'm going with. Optogenetics. Yeah. There we go. So that way you can kind of moderate the neurons using lasers, or modulate. Modulate. It's also good for imaging. So that's pretty cool. Cell-cell interactions. This is something I was looking into. Because I found in a paper I was reading about a specific protein, I think, that it kind of facilitates interactions between neurons. And I was thinking that's perfect because what we need is to like get the neurons to grow in specific ways. So if we modulate the levels of that protein, then I don't know. I don't know. It's complicated. I think I ended up giving up on that particular idea though. I had a better idea, and that's what we're doing now. Oh yeah, I guess I don't have the original paper. See, since I'm creating this so I don't dox myself on this account, but on my other account I have a bunch of other papers, and there's one in particular that was like kind of my basis for all of this. But yeah, I forgot what it was. Oh wait, I might have actually written it in my notes. Ooh. My notes. Where are we? Oh, I see. My face tracking has stopped because I switched apps. Okay, wait a minute. My face is gonna be frozen for just one moment. So this is my idea notebook. Which paper did I reference? Brains on a chip. Oh yeah. Okay. I think that's it. Reversible protein inactivation. Okay, how about we go with, for now we're gonna go with brains on a chip, etc, etc. I think I referenced that earlier with the author name. What was the author name? Aebersold? Whatever. Brains on a chip. Aebersold et al. There we go. Here it is. What is this? Histone epiproteomic profiling distinguishes oligodendroglioma ideation. Oh. I see some epigenetic stuff. That's very interesting. No. Epigenetic is not the same word as eugenic. It's a different word. Epigenetic. The field of epigenetics is very interesting. It's like you have the genome, which is like your DNA, but then you also have some other stuff like molecules and things that interact with it and label it and determine how it's packaged. So that's why all your cells are like they have different identities. So like your skin cells express different genes than your brain cells because of the epigenome. Yeah, I think it's cool. Anyway, can I get this through Sci-Hub? I already have it on my other account, but it would be helpful to have it here. Oh wait, that's Google Scholar. I'm gonna go to Sci-Hub. There we go. Oh wait, it's a manuscript. I don't want that. Sometimes I wonder if Sci-Hub if it can access multiple PDFs, but it only shows you one? I don't know, because it only gives you one result. It doesn't give you a list of results. So that's interesting. Anyway, let's look at the citations. Wait. Wait, am I able to see that? Wait a minute. I'm not sure I can actually see the citations because I can't. Citing articles? Oh, okay. Here we go. I think these are all the citations. Oh no, okay. No, these articles cited that one. Can we reverse it? I wanna switch it. No. Well, this is helpful too, actually. Thermoplasmonic neural chip platform. Thermoplasmonic neural chip platform. Wait, what? That sounds really interesting. What is that? What is that? Thermoplasmonic. Plasmons are quasi-particles of, I think, like plasma fluctuations? Plasmon? Plasmon is a quantum of plasma oscillation. But what is a plasma oscillation? See, is it a spatial oscillation or an oscillation of some other property? Oh yeah, look, phonons. I love phonons. These are basically sound particles. But it's a quasi-particle, so it's kind of fake, but not exactly. Just only in specific situations it maybe exist. Phonons are cool. One of my characters has one of my characters is a musician, and he has something called the phonon synthesizer. It's like a keytar, and it shoots phonon beams, which means he's like shooting laser beams of sound. Which doesn't actually make any sense because phonons can only exist in their media. So quasi-particles, I think, actually can't even leave the medium they exist in. But I just wanted to make a reference. I just thought that would be cool. So it doesn't really make much sense in physics, but also it's in the future. So maybe they figured out a way of extending the medium into a beam, and that's how you have the phonon beam. It's a laser beam of sound. A polariton? Polaritons are quasi-particles resulting from strong coupling of electromagnetic waves with an electric or magnetic dipole carrying excitation. I don't know much about electromagnetism, so that's very confusing to me. Eventually I will understand. I'm getting really into this. Plasmons. So, what is a plasma oscillation? Oh, okay. So here's a Wikipedia article on it. It's known as, I don't know how to pronounce that name. Rapid oscillations of the electron density in conducting media such as plasmas or metals in the ultraviolet region. Ooh. Oscillations in the electron density. Ooh. Consider an electrically neutral plasma in equilibrium consisting of a gas of positively charged ions and negatively charged electrons. Coulomb force pulls the electron. I don't understand this. Anyway. Maxwell equations, those are intimidating. Eventually I will understand. Okay, anyway, we what is this? What is a thermoplasmatic neural chip platform for in situ manipulation of neuronal connections? Oh. I still don't. Okay, here we go. Culture neuronal networks with a controlled structure have been widely studied as in vitro. Yes, this is what I want. Controlling the network structures during cell cultivation. In this study, we present an in situ manipulation platform based on gold nanorod mediated thermoplasmonics to interrogate an in vitro network model. That's cool. We find that it is possible to induce new neurite outgrowths, eliminate interconnecting neurites, and estimate functional relationships in matured neuronal networks. So I think what they're doing is they're shining lasers at tiny golden sticks. So they shoot the lasers at the tiny gold sticks, and the gold sticks do something. There's some kind of physics thing where the light interacts with it, and it does this cool thing, and it causes like a thermal thing that makes the neurons, like, I think it makes their cell membranes kind of break open, and then maybe, I don't know, extend outward. I don't know. It's that's complicated, but this is definitely not what we want because these are neurites. So I think in this case it's like creating these tiny like fake connections between the neurons, which is not what we're actually looking for. See what they're doing? So, see, those are the tiny golden sticks. They look like sprinkles actually. Thermoplasmonic interface. This is the coolest title of a paper I've ever seen. Thermoplasmonic neural chip platform. Wow, that's pretty cool. It's not what we're looking for though. Should we save it anyway? I don't know. Maybe not. That's a bad idea. Let's not do that. Let's not do that. Microfluidic films? Okay. Nah, microfluidics, that's not what we're looking for. Those are like tiny channels, like tiny plumbing networks, tiny tube thingies, to manage cells. But we're trying to make like a whole brain tissue. So that's not what we're looking for. Alginate sulfate substrates control growth factor by. Ooh! I want this one. See this one. The reason why this one's interesting to me is because it's controlling growth factors, and that's exactly what we're looking for. See, we want to control. We want to control the biomolecules that control the neuron growth and placement. So that way we can like modulate exactly where the neurons go with lasers. Control growth finder. Yeah. Sulfated glycosaminoglycans. No, glycosa glycose amino glycans, I don't know if that's right, uh, are vital molecules of the extracellular matrix of the nervous system known to regulate proliferation, migration. Okay, yeah. So these are like important molecules that say like this neuron goes this way. So like when it's growing, it says, okay, this neuron's not gonna go that way. It's gonna grow. It's gonna grow that way. Oh, thank you for the hydrate, Dante, and oh yeah, sure. Thank you for coming, Dante. I appreciate you being here. Thank you for the work. Yeah. So this is. Ah. I don't think this has anything to do with lasers, but this is still handy. A first step is made toward constructing 3D neuronal networks by controllably patterning neurons encapsulated in this stuff into an alginate carrier. The substrates and neural networks developed in the current study can be used in basic and applied neural applications. This looks helpful. Let's get it. We shall download. Here we go. Yes. Wait, were we gonna keep this one? Oh yeah, brain organoid. Brain organoid. Microfabrication techniques. Yes. Microelectrode arrays. Advancements in approaches. Oh. They didn't go into that very much. Modeling I don't know, should we keep this one? Induction of myelination. That sounds like something that needs to be considered. Ooh. So there are these things called Schwann cells. I think I'm saying that correctly. These are like cells that reach out and like wrap around neurons, around their axons, and myelinate them. So it's like they make them conductive. So that's kind of cool. It seems kind of complicated though. But that's how that's biology. Complicated. Myelination of human axons has been much more elusive. Microfluidics. Growth restrictive hydrogels. Okay, so they're talking about making the neurons myelinated, which sounds like something helpful to consider. So I'm gonna keep this one. Anyway, let's add this new one. Yay! Spontaneous functional recovery after phobic. Cluster symbol now structure material. Microfluidic branch. In vitro neural functional connectivity. Microcontact printing from ooh. I think that's good. Maybe. Ooh. I want that one. I want that. Ooh. 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 3D arrays of microcages by 2-photon lithography for spatial organization of living cells. That sounds like just what we're looking for. Kind of, but not actually. In fact, this is actually, I think this is something I was considering, but then I thought it wouldn't really be ideal because, like, you know how neurons, like when they fire, like they have ion channels and they have to have like transport going in and out all the time? Well, I thought if you form a cage around the neuron so that it's forced to grow in a particular way, then that kind of messes up or it seems like it would mess up like that whole ion channel thing, because now where are the ions gonna go? So that might actually mess up the action potential, like the firing of the neuron. So that's why I didn't go with that method. It also just seemed really complicated because you'd have to like scan the laser around where you want the neuron to grow really quickly, so go like and solidify the medium around it, and I don't know, that just sounds really hard, really hard. Yeah, that's why we're going with a much more practical idea. But yeah, I had to brainstorm a lot to come up with this one. This is interesting though. I didn't think anybody had tried this. Self-fixation for scanning electron. Well, actually, I'm kind of skipping everything. Maybe I should go back up. I tend to look for pictures. Yeah, like look at that. See, when I read papers, I like to skip to the pictures because they like show you what's happening. And then that helps you read it. So when you go back to read it, it's a little easier to understand, I think. See, look at that. So they made these microstructures where I guess the cells are gonna be stuck in these. That's really interesting. Like, look, they have holes in them. They have elaborate geometric designs. Maybe because there are holes in it, maybe it would actually work for neurons, because then there would be holes for the ions to get through. Although it still seems like it would hinder the functionality of the neuron just a little bit, at least, like to some degree. It would kind of insulate it. Hypothetically, I actually have no idea. This is just my idea. I'm sure there's some research out there I could find that would tell me if that's correct or not. But that would take a while to find. Also, this is impractical, so let's not do this. It's cool though. Hey, look at that. Look at these look at those nanostructures. Or are they microstructures? Maybe they're microstructures. I think they're microstructures. Oh, my timer is going off. Yeah, look. Oh, my hand is teleporting. It looks like we have to end the stream soon. Maybe in a minute. Perhaps I should go to the talking screen now. Okay, I think I'm gonna switch over to the talking screen. Here. Was this entertaining? I actually had fun. I thought it was fun. Although most people are like studying science, that sounds boring.